I'm very happy to be here. It's not my first time here. I've been several times. I enjoyed this workshop very much. I think it's on the top of my list of this summer's conferences I went to. The topics are extremely interesting, very stimulating. I really appreciate this organization. My topic is multigrid and domain decomposition, similarities and differences. So it's the main solvers that I want to talk about. And I want to start with similarities between these methods. So the first similarity is that both are iterative methods for PDEs. This you all know. The next similarity is both have dedicated conference series to the topic. So there is a multigrid conference. It was the 19th Copper Mountain Conference that I went to this year. There is also the European Multigrid Conference. It's now called the International Multigrid Conference, and this year it was in China, in Kunming. There is the 26th Domain Decomposition Conference going to be in Hong Kong. So you see there is a lot of things happening in China. So that's another point in common. Both are optimal methods. And optimal has here a mathematical definition. So this is a copy from the book of Toselli and Widlund. Definition 1.2, optimality. An iterative method for the solution of a linear system is said to be optimal if its rate of convergence to the exact solution is independent of the size of the system. This is something you can check, you can prove for methods, but it doesn't mean you have a good method. You can have an optimal method that is 100,000 times slower than another optimal method. They just do not depend on the size of the system. So optimality doesn't mean it's good. So if you have a paper that claims there is an optimal method in it, and it uses this definition, you still should very carefully read the paper and study if it really is a fast method or a slow method. So these two classes are both optimal. That's what I'm coming to now. So this optimality result is based on the Laplacian, basically. The generalization of this method to non-symmetric problem, advection, diffusion, for example, is not trivial. And to wave propagation problem, the generalization is hard for both types of methods. For domain decomposition, we've seen there is quite some progress. For multigrid, it's basically stuck. There is no good multigrid method for a wave propagation that I know of. There is another direct relation that I'd like to mention here. It's a beautiful relation that goes back to Jinchao Xu in this seminal paper, Iterative Methods by Space Decomposition and Subspace Correction in SciRef in 1992. And he explained to me the idea that he had when he tried to link these methods. In domain decomposition, you have subdomains, and in general, you have many unknowns in each subdomain. Now imagine that these subdomains become smaller and you have less and less unknowns. And at some point, there is just one unknown left. Then if it was a Schwartz method, you have now a point Jacobi method. So there's a direct relation between a point Jacobi iterative smoother and the Schwartz method. That's the link he exploited in this paper. So there's a direct relation between these methods. But to explain more about these methods, I'd like to start by explaining the methods. And for me, I had in my title, it's a personal view on this subject. For me, multigrid methods are essentially discrete methods. They have already grid in the name. They're based on a discretization. They're made to solve a linear system AU equals F. And this system comes from a PDE. It comes from a discretization of a PDE. But it's a discrete system. And here is a multigrid method, a classical multigrid method. It's not complicated to describe. You first start with some initial guess, U0. You apply some smoothing steps. Here it's nu1 smoothing steps. This can be a point Jacobi with a relaxation parameter. Otherwise, it's not a smoother. Or it can be Gauss-Seidel. That doesn't need a parameter to be a smoother. You do a few steps, you get a new approximation. Then you calculate the residual, F minus AUN. You restrict this residual to a coarse grid. You do a coarse solve. You prolongate that solution that you obtained to the fine grid, and you add the correction. And then you might do some post-smoothing, new 2 post-smoothing steps, like you had pre-smoothing steps. Here you get a new approximation, you iterate on this. Prolongation is naturally done by interpolation. You want to go from a from a coarse to a fine grid, you interpolate the nodes in between. Restriction can be the transpose of prolongation. That's a natural choice. There are also other restrictions. And the coarse matrix, you can choose a Galerkin approach, so use your prolongation and your restriction from the big matrix to get the small one, or you can rediscretize. That's a standard multigrid method. These are all components that are needed. How does it work? Here is the example that I will use throughout my talk. It's an academic example. It's on a unit square, but it represents a small room, a student room. So you have 0 temperature on the walls. So it's pretty cold. It's not well insulated. But you have a door. Luckily, there is a door, and the door goes into a warm hallway. So here the door is warm, and this warmth goes also a little bit into the room. And also this wall here is connected to a hallway, so it's also a bit warmer than the outside part. And he has a heater in the middle, so he can heat the room a little bit. So that's the distribution of this temperature in the room. It's a solution of a Poisson equation. So I apply multigrid to this. It's a V cycle. I go down to one unknown. I use a Jacobi smoother. I use a damping parameter 2/3, one pre and one post smoothing step. This is the first iteration, second iteration, third iteration, fourth iteration, fifth iteration. Now you see we're basically converged. It's a fast solver for this problem. What results do we know about multigrid? The first result goes back to Fedorenko in 1964, and it's a result that I like very much. It's based on Fourier analysis. It gives a lot of insight into the functioning of this method. I consider Fourier analysis like the Swiss pocket knife, the Swiss army knife for numerical analysis. It's a small tool. You get a lot of information, very precise. You might not be able to haul a big truck with it, but a lot of information. This is Fourier analysis. Then in 1979, Hack-Busch came up with a very general convergence estimate for multigrid, and he writes the multigrid iteration in one step. You see there's a UN plus 1 of my previous algorithm related to UN with a matrix G, and here you see the components that I had before. There is the smoothing, the residual calculation, the coarse grid correction, and then added as a correction. So this is exactly the algorithm I had on the previous slide, except it's written in one line, and I don't do post-smoothing here because Hack-Busch also in his original paper didn't do post-smoothing. He just considered the pre-smoothing step. And he has a contraction estimate for this method. And the contraction estimate sets for any contraction rate you want. For example, you want the error to be multiplied by 1/2 in each iteration, or by 1/10, or by 1/100th. Any contraction you want. There exists a number of smoothing steps, new, such that you get it. This iteration contracts in the norm at the rate that you want. And Michael Griebel in his PhD thesis in 1990 calculated how many floating point operations you need for this V cycle, independent of the size of the problem. And it's 23. Now I remember this from a talk a long time ago, but I didn't have the formula, the precise number, so I sent an email to him 2 months ago, and he answered, and he told me this is a result from my thesis. And then I said, can I get your thesis? And then he said, I'm going to try to dig out a copy for you. And he sent me a copy. And it's very nice because this is for the 5-point stencil finite difference Laplace. And he also asked for other stencils. So the numbers are slightly different. Slightly different.
One smoothing step?
This is for, no, not one smoothing step. It's a full V cycle, one V cycle. Per unknown, it's 23 floating point operations. Yeah, the smoothing step goes into a factor. I think it's 2 in this. No. So this is a truly optimal result somehow, because if you know that this contracts independent of the size, then you get a very, very good solver for these systems. It's very hard to beat a solver like this. It's a very, very good solver. Now, domain decomposition. What's domain decomposition? Domain decomposition for me is essentially a continuous method. I don't need a grid to define a domain decomposition method. All the methods I know I can write at the continuous level, at the PD level. So here is the Schwartz method. The Schwartz method was a tool to prove a result in analysis, to close the gap in Riemann's PhD thesis at the end on the Riemann mapping theorem, invented by Schwartz. So here is the original example. We've seen this once already in the conference. There is a domain that's composed of a disk and of a rectangle. And Schwartz wanted to solve a Laplace equation on this with given boundary conditions. And this alternating Schwartz method, it just looks at the domain as two overlapping subdomains of simple shape, a disk and a rectangle. And then you solve on the disk. You don't know what the value of your solution is along gamma 1. You put something, 0 for example, and you find a solution on the disk. Then you trace this solution on the boundary of the rectangle. You impose it as a boundary condition on the rectangle. You solve. You have a solution on the right subdomain. This is not going to be the solution of the original problem because you started with the wrong data. But you can iterate on this. So you see this is the alternating Schwartz method. No discretization. This is all at the continuous level. Schwartz proved convergence of this using the maximal principle. It's not a parallel method. It's a sequential method. You solve left, right, left, right. But Lyons, about 100 years later, introduced the idea to just start on both domains with some data, 0. And you solve on both domains. Then you exchange. You solve on both domains, you exchange. And then it's parallel. And you can imagine if you have many subdomains, you can use many processors. That was the idea of Lyons to introduce this change. So this is the parallel Schwartz method of Lyons, this. Whereas the other method was the alternating method of Schwartz. So here is an example, the same example as before with the temperature in the room. I'm first going to do a alternating Schwartz method. So I have two subdomains. I have a subdomain on the left part of the room, subdomain on the right part of the room. I have overlap between 0.4 and 0.6, and I iterate. So here is the solution on the left subdomain. I start with 0, like Schwartz. Then solve on the right, solve on the left, solve on the right, solve on the left, solve on the right, solve on the left, solve on the right, and so on. And you see it converges. Now I do the parallel method. So I solve on both subdomains. I exchange data, solve, exchange, solve, exchange, solve, exchange, solve, exchange. You see it's a bit slower. I need about twice the number of iterations. This is because the parallel method calculates two alternating sequences which are just embedded. You can see it just goes like this. For two subdomains, it's a direct relation. For many subdomains, it's not so direct a relation. What convergence results are known about these Schwartz methods? The first result I told you about, it's due to Schwartz. It's done by maximum principal arguments in 1869. We also had a quote 1870 in this workshop. The talk was given in 69 and the publication appeared in 70 of Schwartz. Then Lyons, about 100 years later, came up with a completely new tool, variational analysis, based on projections. It's a very, very interesting approach to study convergence of these methods. Then we have Chan and Rosasko, who introduced Fourier analysis to study methods of this type. And then Lyons, in 1999, also gave a maximum principal proof. So you can wonder why are there two maximum principal proofs? Because there is an inaccuracy in the proof of Schwartz. There is a study where he was not very careful. He just claimed something is true, and Lyons actually shows exactly why it's true. So it's a more accurate estimate. And then there's a very, very interesting paper by Bramble, Pashiak, Wang, and Zhu in 1991, where they have both continuous and discrete orthogonal projection estimates. So they go using techniques of Lyons. And all the results in these papers give contraction estimates, exactly like for multigrid. These are iterative solvers, and they contract at a certain rate, and the contraction rate is estimated. They're all at the continuous level as well, except there is also in Bramble, Pashiak, Wang, and Zhu some discrete estimates as well. Now there's another method that was invented around the same time, and this is the Additive Schwarz method. This was invented by Dria and Widlund in 1989. It's a discrete method, and they have a two-level condition number estimate. So it's a two-level method, and they have a condition number estimate that says the condition number of the preconditioned matrix is bounded by a constant plus 1 divided by capital H over delta, where delta is the overlap of the subdomains, and capital H is the size of the subdomains. And usually in an application, this overlap will be a few mesh sizes. You could also have very general overlap. We've seen methods like this, when this is proportional to capital H. So for Additive Schwarz, there is a condition number estimate. There is no contraction estimate. So that's the first interesting difference. Now, this estimate is a discrete estimate, but I told you this method, domain decomposition methods, can be defined at the continuous level. So does this hold? It does. You can prove that this estimate also holds if you don't discretize. There's no fine mesh. You get the same result. The estimates can be done. They're technically not so easy, but they can be done, and we have a result on this from 2014. So this estimate also holds at the continuous level. Then there are the Neumann-Neumann and FETI methods. We've seen a lot about the FETI methods. The Neumann-Neumann method goes back to a publication by Bourgat, Glowinski, Le Tallec, and Vidrasco in 1989. And I'd like to give you the method exactly like they describe it. It's a method that has two major steps, and I just describe it for two subdomains like I did for the Schwarz method. So how does this method work? You have to start with some guess at the interface between the subdomains, and there is no overlap. So it's not like Schwarz, there's no overlap. You take some guess for the solution, like in Schwarz, 0 for example, which I call H, and then you solve two Dirichlet problems with this boundary condition, because now you know what the solution is at the boundary, so you can solve on both subdomains. So you obtain approximate solutions Ui. And then you follow with a correction computation. What is the correction computation doing? You take the traces, the normal derivative traces of these two solutions you calculated, and you add them, and you impose this as a Neyman condition to the equations in the subdomains, and no source here. It's a correction, so there's no source. And you calculate 2 psi. So each step takes 2 Dirichlet solves and 2 Neyman solves. And once you have these solutions psi, you take their Dirichlet traces, you sum them, and you add a relaxation parameter, and you calculate the new Dirichlet trace at the interface. So you see exactly how it works. You start with some data, you solve Dirichlet, you do Neumann, you solve Neumann, you have a relaxation, you have a new Dirichlet data. That's the Neumann-Neumann method. We've heard a very nice talk already by François Xavier today about the FETI method. The FETI method was invented in a quite different setting from the way we've seen it. It was invented by imposing the problem as a minimization problem. It comes from a variational formulation, so you don't look at the Euler-Lagrange equations, which are the Laplace equations. You look at the functional to minimize. You cut the domain into 2. You say we want to minimize only in the subdomains, but then it's not consistent at the interface, so you introduce Lagrange multipliers to make it consistent. That's how the method was invented. But this method is essentially doing the same as this method, but in the other order. You start with the Neumann data and Neumann solves, and then you do Dirichlet corrections like it's done here for Neumann, and you have a relaxation step. So these methods are very, very much related. So how does it work on my example? I just showed the Neumann-Neumann, the FETI would be very, very similar. I start with a non-overlapping decomposition, a smaller subdomain and a bigger subdomain, and I start with a 0 approximation, and I solve the Dirichlet solves. That's what I get. Now I take the normal derivative at these, I sum them, I do Neumann corrections, and I add them and do a Dirichlet solve again. So that's the next step. Wow, you see? That looks almost like the solution. So I do another one. So you saw it overshot a little bit. I do another one. Not much changes. It's a very fast method. So what happens if I take subdomains that are exactly the same size? So I cut exactly in the middle. And I remind you, this is a Poisson equation. Same operator, same subdomain size, same boundary conditions, Dirichlet all around. So I do one correction, and I have the solution. This is a direct solver for this configuration. It's a direct solver. If I do once more, it doesn't change. That's Neumann-Neumann. FETI has exactly the same properties. What is known about these methods? What is known about Neumann-Neumann? There is a result by De Ruyck and Le Tallec in 1991. They have a continuous analysis for this method. There is a continuous analysis that shows that the method contracts, but there are no cross points in this analysis. And with cross points, there is discrete analysis. And then there is again a fundamental condition number estimate that goes back to Mandel and Brezina. And you see it looks like the Schwarz estimate. The condition number of the preconditioned system is bounded by a constant times 1 plus a log term of capital H over little h. This is a discrete estimate. And the big domain size and the mesh size come in this estimate. And there is a similar result also by Jan Mandel. It was very fundamental contributions here. Just a little later, for FETI, a very similar condition number estimate. And here it's really appropriate to mention that Axel has worked tremendously on moving the theory of these methods forward. He was instrumental. There are papers with Olaf, papers with Reinbach, paper with Max Trier. There is a lot of contribution that we heard Axel talk about the FETI methods today as well. There's a lot of important analysis for these methods. Again, I'd like to emphasize these are condition number estimates, whereas only in the first paper without cross points there was a contraction estimate. So we've seen two differences so far between multigrid and domain decomposition. For me, multigrid, as I told you, is defined at the discrete level. It's a discrete method. DD methods are defined at the continuous method. The continuous level, they're continuous methods. That's for me a fundamental difference. The second difference is that we have contraction estimates for multigrid. They're all contraction estimates. We have contraction estimates for some domain decomposition methods, but there are a few of the very popular important methods that do not have contraction estimates. They have condition number estimates, and Additive Schwarz is one of them. Neumann-Neumann with cross points is one of them, and also FETI with cross points is one of them. So why do we have condition number estimates for these methods, whereas the methods, as I've shown you, they just contract? They're PD methods, they just contract. Why is that?
The question was, so if you have a condition number estimate, all of these methods would be used in the discrete sense with conjugate gradients, and therefore you could immediately turn a condition number estimate into a contraction estimate.
I will get to that. Yes, yes. So let's look at Additive Schwarz for the temperature in my room. So I do Additive Schwarz with the same two subdomains I've shown you before, alternating and parallel Schwarz. And I just iterate. First iteration, second, third, fourth, fifth, sixth, seventh, eighth, 9, 10. You see it's not converging. There's not a convergent method. Additive Schwarz as an iterative solver is not a convergent method. It was not advertised as a convergent method. It was advertised as a preconditional. But I think this is important to know. So this is very different from the solutions I've shown you before. What happens if I use more subdomains? Let's say I use 25 subdomains. I solve the same problem, and now I indicate the subdomains here. So you can see I have 25 subdomains, 5 by 5, and I use Additive Schwarz in this example. First iteration of Additive Schwarz, you see already here at my door, there are overshoots in the overlap. I have overshoots here, and here I start heating. Now if you look at the iteration of Additive Schwarz as an iterative solver, you see these cross points are extremely bad for Additive Schwarz. It's not converging. But we have a condition number estimate. So there is a bound on how bad this goes, and a Krylov method can take care of this. But as an iterative solver, it cannot be used like this. So you see divergence is very violent. 9, 10.
Yeah, but that's what I'm just doing.
I get to exactly, I just wanted to say now, I learned from Daniel Schild about 15 or 16 years ago that there is a linear algebra community where this is well known. And you can introduce damping in the method. And if you damp the method, then you can make it converge. So I damp it. So I introduce a damping which is strong enough to bound these modes. So now this is the damped Additive Schwarz iteration. And I damp. And now you see these oscillations are still there, but they're controlled by damping. So I iterate. You see it works. And in 20 iterations, I get to about the height of the last red line. Now what happens if I use the parallel Schwarz method of Lyons on this example? Because that one does work. So I just do it. This is now the parallel Schwarz method of Lyons. We just iterate. No problem. There is a proof that this converges by maximum principle. And you see in 20 iterations, it converges to a much more accurate solution. Because the damping that you need to damp these divergent modes, it also harms the convergence of the method. But it's very important, Additive Schwarz was never advertised to be used like this. It was advertised to be used as a preconditioner. But I think it's important to know. What happens if you use Krylov acceleration? Here is a comparison. Here is the number of iterations. Here is the error. And here are two curves. There is a curve which I call RAS, and there is another curve which I call AS, Additive Schwarz, or restricted Additive Schwarz. So you see the Krylov method needs to do some work to remove these modes that Additive Schwarz produces. But it converges. It's a good method. But if you use RAS, it takes less steps. So it's beneficial to have a method that converges as an iterative method in this situation for the number of iterations. So again, it's very important. Additive Schwarz is a preconditioner. It was never meant to be a stationary solver. But if you have a good stationary solver, like RAS, you need less iterations. Now I should tell you about RAS. RAS is the correct discretization of the Lyon's parallel Schwarz method. If you apply RAS, you get exactly the Schwarz method that Lyon's designed. So this is the method that you've seen on the previous slide, iteratively. RAS, restricted Additive Schwarz. If you want to read about this, it took quite a while to understand this. This is a paper which is very easy to read, just 2 or 3 subdomains. And this is a paper that proves it in full generality. And I'm very happy these papers are now cited more and more. I think people want to know about this. They want to know why RAS is better than Additive Schwarz. Now let's go to Neumann-Neumann. I also told you Neumann-Neumann has a condition number estimate, no contraction estimate, as soon as there is a cross point. And here I show a result that's due to my PhD student, Faisal. I actually implemented this myself this summer as well. And it was just before coming to this conference, I wanted to add the coarse correction that I want to show later. I did not manage to quite finish, so I showed the calculations that he did. This is now not my room, but it's also on a square. It's cut into 4 subsquares, and I run the Neumann-Neumann iteration with a cross point. And I start with this initial guess. It's a smooth initial guess, and the solution is the bump that we want to calculate. And I run it as an iteration, stationary iteration, exactly like I described it. Now you should look at the scale here as well, why I iterate. This is the first iteration, second iteration, third iteration. Look at what happens at the cross point. Fourth iteration, we're at the scale 10 now. Fifth iteration, we're at the scale 30. This is also not converging. That's why there is a condition number estimate. There is no contraction estimate. But here the situation is much, much more severe, because this method is not well posed in any function space if you look at it at the continuous level. You cannot find a functional setting such that this method is well posed. And the problem is that you have Neumann traces which give you new Dirichlet traces which are discontinuous at the cross points, which you will solve and then take Neumann data from a discontinuous Dirichlet trace on the boundary. This is going to have a singularity, for which you impose a Dirichlet trace again after you've averaged. This method has no chance to work as an iterative method. But again, this growth is controlled. This gives you the log term in the condition number estimate. So that's why these methods are preconditions and are not stationary iterative methods. But I like these methods at the PD level, so I wanted to write this method at the PD level. And it's possible, but you have to add a correction. And here what we do is we do a coarse correction, not for scalability. It's to fix the method. And then you get a method which is well posed in H2. This is a very recent result. Even if you have a cross point, and if you run it iteratively, exactly the same example, but now with this is a local coarse correction. It doesn't do global communication. Then you get a method which converges. Again, you can wonder, is this important? The Krylov method fixes it anyway. And it's true, it fixes it. This is without this local coarse correction, and this is with the local coarse correction. So it does help. You take less Krylov iterations. You also pay something for the local coarse correction. It's not free, but it's not an expensive correction. It's not a global one. So now there is a method which I have not shown you yet, but it's a method that has been mentioned very often here in this meeting. It's the optimized Schwarz method. And it's a method that goes back to Lyons as well. It's amazing what Lyons had in the 3 papers in the early days of the DD conferences. Just amazing. The idea is a very simple one. You remember what Schwartz did? He just took Dirichlet data at the interfaces. And what this Lyons proposal is, you take a combination of Dirichlet and Neumann data at the interface. That's the only difference. You can do it in parallel, like I showed you for Lyons. You can do it alternatingly, like the alternating Schwartz method. It's a new class of methods. There's an early result by Frederick Natoff that shows that if you have 2 subdomains, and if you use for this parameter here at the interface, which acts on the Dirichlet trace, the Dirichlet to Neumann operator, this is an expensive non-local operator, you get convergence in 2 steps. It's a direct solver. This is like the Neumann-Neumann method if you're exactly in the middle, but it works for any position of the interface, and it works with and without overlap. So this is a very general early result. And in addition, he shows that if the decomposition is a strip decomposition into J subdomains, then you have to iterate J times with this parallel method, and you still have a direct solver. After J iterations, you have the solution. Only more recently, we realized that in this case, when you use the Dirichlet to Neumann operator as the parameter, and if you do an alternating method, so you go from left to right, and then from right to left, it also is a direct solver. And in that case, there is a very nice relation of this method to linear algebra, because you can show it's the exact block LU decomposition of the matrix, but written at the continuous level. So these Dirichlet to Neumann operators, if you wrote your matrix, you did a block LU decomposition, you would see Schur complements appear, and these are the Schur complements which are here, the Dirichlet to Neumann operator. So how does this work on my example? Here is first an example with 2 subdomains. I do an optimized Schwartz method, so I just have a number, and we have formulas what a good choice is for this number, for many, many equations. We know many equations. So this is a Poisson equation, so we know what the formula is. This is the first iteration. It's a parallel version. Second iteration, third iteration. You see, this is a very fast method. Cost per subdomain is the same. It's just a Robin condition instead of a Dirichlet condition. Now I'd like to show you what happens at the cross point with this method. So here I show you the error so you can see. And there is a decomposition into 4 subdomains, and there is a cross point. And I've shown you FETI and Neumann-Neumann as an iterative method. They have a problem at the cross point. So here is an optimized Schwartz method. We iterate. You see, these are contracting methods as a stationary iteration, and they're well posed in a function space. Now, this idea of optimized transmission conditions has been reinvented over the past years by many, many researchers and scientists. Here is the list. The last one I discovered, it's also an optimized Schwartz method, is an algorithm by Bank and Zsimak in 2001 that has an analysis in 2008 by Bank and Vasilevsky. Then there is analytical incomplete LU. This is where a relation with this block LU decomposition was made, but I didn't yet see it's exactly the block LU decomposition in the sweeping sense. Then there were the sweeping preconditions by Enquist and Ying, their optimized Schwartz method, where you use a PML to approximate the Dirichlet to Neumann operator. There is the single layer potential method by Stalk in 2013. There is the source transfer method by Cheng and Jiang. And when I met Jiming Cheng, he's from the Academy of Sciences in China, I asked him why they invented this method, because I didn't understand the method yet. And then he said, we couldn't understand the sweeping precondition of Enquist and Ying. And so they came up with their own method, called it source transfer domain decomposition. There's the method of polarized traces from the MIT school. And it takes a mind-boggling effort to understand these methods, because they're invented in different settings. For example, this one here is invented, the source transfer is in a DD setting, but with Green's functions formulations. The sweeping preconditioner is invented in a discrete setting, not having subdomains, but just grid lines. It's very difficult to link them. And it took us about 5 years to show that all these methods are based on the same mathematical principle. At the continuous level, it's this optimal Schwartz sweeping method. And at the discrete level, it's the block LU decomposition, the exact block LU decomposition. There's a paper that just appeared now in SIAM Review. A simpler introduction is given in 2006, but I had no clue yet about all these further relations. These algorithms were not there yet. So let's look on my room what happens if I do one of these sweeping types. So I need more subdomains now. So suppose I have 4 subdomains in this direction, and I sweep in the room. And I use the optimal Schwarz method, the one that has the Dirichlet to Neumann map. So I start on the left subdomain, and I go, and then I come back. I must have the solution, and that is the solution. So it's just one forward solve and one backward solve. That's an optimal Schwarz method. Now I can use an approximation. For example, I use a Robin condition with the p that I know what its value is. So I go forward and backward. It's pretty good. But this is not the solution. It's not the exact block value decomposition. So I go once more. And you see it does correct a little. And can go once more. It still corrects a little. And now we're converged. So these are very fast methods. And most of these methods were invented for Helmholtz. But it has nothing to do with Helmholtz. The fundamental structure is the block value decomposition or the optimal Schwarz method. PDE is completely irrelevant. Let's look at the classical Schwarz method, alternating sweeping. That one is not very fast, you can see. But I remind you, this is also an optimal method. If you fix the overlap and you find the mesh, the number of iterations is not depending on the number of unknowns. But it's a much, much slower method. Much, much slower. I think I stopped at some point, I hope, maybe at 8 or so. Yes, I did. Okay, so I've shown you 2 main differences so far. I've shown you discrete multigrid versus continuous DD, and I've shown you contraction estimate versus condition number estimate. There is a third major difference for me. It's coarse spaces, coarse space corrections. And I want to explain this in the remaining time. So what's the coarse correction that's needed in a multigrid method? In a multigrid method, the coarse correction is based on what's called an error equation. And here you see the error equation. I have AU equals F, and I add and subtract my approximation UN. And the error is U minus UN. So I get A times the error is A times my approximation equals F. And so I can put the AUN on the right, and I find what's called the error equation. A times the error at step n equals the residual. And the coarse correction is based on this error equation in multigrid. So what do you need to do with this error equation? You could just solve it. If you solve it, and if you add this error to the solution, to the approximation, you have the solution, you're done. That's the best you could do. But that's as expensive as solving your problem. So you need to get a cheaper way to do this. And what you do is you look at some Jacobi smoothing steps, which you do before you do the coarse correction, and you look what's left in the error. This is what I plotted here for the room example. So if I do 3 Jacobi smoothing steps with the damping parameter 2/3, that's the best damping on the high frequency for Jacobi, then I get this in the error. And you see it looks rather smooth. I started with a random initial guess, so there's a lot of oscillations initially. It looks rather smooth. And here is the residual. And so the idea in multigrid is because it's a Laplace equation, you have this property from Jacobi or Gauss-Seidel, and you approximate this error on a coarse grid, and you solve this problem on a coarse grid. That's a good coarse correction for multigrid. Now, how does this look like in domain decomposition? So what does one classically do as a coarse space? There is a quote from the book of Toselli and Widlund as well. The subspace V0 is usually related to a coarse problem, often built on a coarse mesh. That's what we usually do. Like in multigrid, we build a coarse mesh, we do a coarse solve in the residual equation, and then we interpolate. But look at what happens in the error that I obtain if I do one parallel Schwarz iteration with a random U0. You see it also looks smooth. But it's not smooth in the same sense as multigrid. You see in the subdomains it's extremely smooth. These functions are harmonic in the subdomain. But between subdomains there are jumps. And if you look at the residual, it looks completely different from the multigrid residual. This is the residual. The residual is 0 within every subdomain. Why is this? Because domain decomposition methods solve the problem in the subdomain. There is 0 residual left. The only place where you can have residual is where the domains are connected. So you see what the shape of the error is, and you also see what the shape of the residual is from this experiment. So I'd like to show you what the error equation is for domain decomposition, like I've shown you for multigrid. So we know that any domain decomposition, this is FETI, Neumann-Neumann, Schwarz, optimized Schwarz, no matter which method you take, it solves on the subdomain the problem. It's LUJN equals F. That's what these methods do. And so if you define the error like I did it for multigrid, it's the solution minus the approximation. Then you see if you apply the operator, independent of the PD, if you apply the operator to this expression, then you get L times U, which is F, and you get L times UJN, which is F, so you get 0. That explains why the error is always harmonic. That's why it looked so smooth in each subdomain, the error. It's a harmonic function, which means it solves your homogeneous PD, no matter what your PD is. It solves the homogeneous PD. So from this, you can immediately define what an optimal coarse space is, and not optimal here in the sense of scalability or in the sense of number of iterations. Optimal in the sense there is no better space. This is the best space you can choose. So what's that space? You just need all piecewise harmonic functions in each subdomain, because that's where your error lies in, no matter what your DD method is. Now what's the equation? What's the error equation that one has to solve? From the approximations that we calculated, we can calculate the Dirichlet jump, and we can calculate the Neumann jump, because we know the UI and UJ on each interface. And so what does the error satisfy? The error that we've seen on the previous slide. The error satisfies the homogeneous equation in each subdomain, and at each interface, it satisfies a jump relation. This is called a transmission problem. We've seen transmission problems earlier in this conference as well. So if you solve this problem, the solution lies in this space, and then you have the solution of the DD method after the next step. This is the exact error equation like in multigrid. That's the one. If you solve this one, it's a direct method. Yes? Is it non-overlapping or overlapping? Or is it gamma JI strict? It's a very, very good question. So this works for any method, overlapping or non-overlapping, but the correction in the coarse space is done in a non-overlapping setting. So you use the subdomain solutions in a non-overlapping decomposition, and the jumps are posed at the non-overlapping interfaces. Now this problem can be simplified. If it was a Neumann-Neumann method, you know the Dirichlet jump is 0. If it's a FETI method, you know the Neumann jump is 0. So you get a reduction in the size of the problem. But this is the exact equation that the coarse space should solve. So how does such a coarse space look in 2 dimensions? Here is an example. There are 9 subdomains, 3 by 3. I construct overlapping ones, but like Rob said, I also put the lines here of the non-overlapping decomposition, because that's where the coarse space correction is applied. And so the optimal coarse space in this case, it's a very big coarse space, because you need all the traces to the left of the subdomain boundary and to the right of the subdomain boundary. And then you need, for each of these degrees of freedom, the harmonically extended function to have all discrete harmonic functions. And in that space, you find the correction in one go. It's a direct solver. Now that looks very expensive. So I'd like to first show you an experiment. This is again the example I had. It's an optimized Schwartz method. I could do this with any other method as well. I have one cross point, and I show you only the error again. We've seen this already, but now look carefully what's left when I iterate. Look at these functions. We know they're harmonic because it's the error. That means they satisfy the equation, but they have a very typical shape. They're Q1 functions. Why do I know these are Q1 functions? Because all these Schwartz, Dirichlet, Neumann, Neumann methods are smoothers. This is somehow the bootstrapping process you've seen in algebraic multigrid. You see, I've run the method 3-4 times. This is what's left. It's a Q1 function. I know this a priori for this Laplace equation, so I know what it is. So I just put a Q1 function in my coarse grid. So I put 4 Q1 functions that I correct in each iteration. That's the first correction. You see these Q1 functions are gone. But you see a second function appearing. Look carefully at the interface here, 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 and here. I started with random, so there is noise, but this is a smoother. So the second iteration, third iteration, these are sine functions. It's the first sine on this edge, the first sine on this edge, the first sine on this edge. We've seen in the talk by Axel, the sine is the solution of an eigenvalue problem along this interface. For the Laplacian, it is a sine function. So this space could be enriched. I can put the sine function, then this one is gone as well. But then what's left is the second sine function. If I put the second one as well, a richer coarse space, there's a third sine function. It's just a spectral basis of my very rich space that I've shown you, which has too many points. So if I compare various Q1 spaces now, I could have a Q1 coarse space that has a degree of freedom in the middle of every domain. I could have a Q1 space that has at each cross point a degree of freedom, or I could have 4 unknowns in each subdomain, it's a richer space, or I could put 4 points around each cross point. We've seen which one approximates the best space. It is this one, because if I put all the nodes, that's what I would need. That's why the Q1 was a good function for the Laplace. And this you see immediately if you run this as an iterative solver. So this is an experiment now with 16 by 16 subdomains. It's the parallel Schwartz method of Lyons. I implemented it as RAS. Here is the number of iterations. Here is the maximum error. And you see if you put these Q1 functions, you get a much faster convergence than if you put any other option of a Q1 coarse space. This is really an approximation of this optimal coarse space. Here is a comparison that was calculated by Serge van Kriekingen, who is a researcher at IDRIS. And I'd like to mention how I got to know him. I had never met him when he sent me an email. And he said, don't you think one should do a careful comparison of these methods that one person implements in one software package and tests? And I said, oh yeah, great, that would be fantastic. And he said his boss allows him to do this on the side. So he would like to start. And then we started to have an email exchange. And it went over a year. And after a year, he had comparisons of all these methods. And I realized the guy is very good. He's a very clever guy. He understands the methods. He can code them. And so I invited him for a seminar. And we discussed the results. And we were working in the meantime on non-symmetric problems, because all these ideas apply to non-symmetric problems. But here are results for a symmetric problem. So this is all results that were done in PETSI by Serge van Kriekingen from IDRIS. And this is a scaling experiment. We have 200, 400, 800, up to 1,000 subdomains, which means processors. It's a PETSI implementation, and these are iterative methods, no Krylov for the moment, so I cannot show additive Schwarz on this. So this is just the parallel Schwartz method. On the top line is the parallel Schwartz method with a classical coarse correction, which means one unknown per subdomain in the middle. Then the next line in blue is the classical parallel Schwartz method, but now with an optimized coarse space, which is the Q1 coarse space, which has 4 nodes around. It's just on a square. And then here is an optimized Schwartz method with a Robin transmission condition, but the classical coarse space. And here is with optimized transmission conditions and optimized coarse space. So you see all these methods are optimal. But some are more optimal than others. You see? But multigrid is still faster. The number of iterations, multigrid is faster in number of iterations on this problem. Yes?
So one thing you haven't discussed, and now is the question, you haven't said that some of the multigrid methods like hyper are not converging, and you can't really do a construction analysis either, because algebraic multigrid methods are not strictly speaking.
On this Laplace problem you can actually do. Okay. It's very simple. Yeah. But for a general problem it's much harder. Yes.
With Richardson.
Yes. This is no Krylov, no nothing, just stationary iteration. Yeah. So what happens if you use Krylov? Everybody becomes faster because Krylov finds a better polynomial. And now I can also show additive Schwarz. So in red, there are lines added for additive Schwarz. And additive Schwarz is symmetric. I use conjugate gradient. Whereas for the other methods, they're non-symmetric. I need to use GMRes. But you see number of iterations, even though you have a better Krylov method, additive Schwarz is paying for these cross-point divergence modes. So number of iterations is slower than the parallel Schwarz method of Lyon's. Optimized Schwarz is still faster, but here I use Krylov as well, so it's still, multigrid is much lower iteration count. So let's look at CPU time, because now there's the same guy who's implementing, it's the same guy who's testing. Here is CPU time. Same experiment. You see the parallel Schwarz method as an iterative solver with the classical coarse correction. It's by far the slowest method. If you put a better coarse grid, it's already a much better method. If you use optimized transmission conditions but the wrong coarse grid, it's still better. And with the best coarse grid, it's better than all of them. And now you see that multigrid is paying in communication time. That's a well-known problem of hyper. It happens also with the geometric multigrid, but I think one could tune there. If I use Krylov on top, then all the Schwarz methods come down. You see, Krylov really helps a lot. Now they're all better than the multigrid method that we tested in wallclock time. And if you blow it up, you see the same hierarchy basically remains. So you have the optimized Schwarz method with an optimized coarse grid, which is the fastest, whereas classical coarse grid, classical transmission conditions are the slowest.
Should you have taken the real estimate of 33 operations?
Here I just ran the solver in the package.
I mean, isn't it unfair to use for the multigrid
No, we have the geometric as well. It's just not on this plot, but I have it as well. It's very similar. Yeah. No, this is the best that I can find. But I would probably need to work on tuning. It's the standard package.
Yeah, like I said yesterday, I think for multigrid it really is very crucial what you do in the course.
Yes. So I did both geometric and algebraic. Yeah. I don't want to say multigrid is slower. This is by no means what I want to say here. I mean, I told you at the beginning, for me, multigrid for Poisson is very difficult to beat. This is really good solver. This is just how it came out in this comparison. And it was with both packages.
Question.
Yes?
What's for this on the previous slide?
Previous slide.
Either way.
Okay.
So the special coarse grid correction.
It's just the Q1 here. No other enrichments. One could further enrich, but it's just the Q1 I've shown you.
Right, but it seems that from everything you've shown, that it almost doesn't pay off. That you have to work much harder just to get a little bit.
No, you don't work harder at all. If you look here, it goes from this blue line to this blue line. If you have an asynchronous method, you cannot use Krylov.
Optimized Schwarz.
Oh yeah, for optimized Schwarz, it's much less. This is classical Schwarz.
Right.
Yes.
But if
Yes.
you optimize Schwarz, you might as well do the simple thing. It's not that much different.
But you could, but it's not more complicated. It depends where you put your nodes. This is really not complicated. You can choose your nodes in the middle, or you can choose your nodes at the cross point. This is really not more complicated. It's the same code, same right. It's really not complicated. But the important thing is you could enrich it as well. So I show you results with enrichment on a more difficult problem. So this is now a problem which has high contrast, like Axel had it. You see there is high contrast that crosses interfaces. This is an example where we still have rectangles. But you can imagine now that the domain can have an arbitrary shape. You will still get not a Q1 function, but a function that's 1 at the cross point, going linearly down to 0 if it was a Laplacian. Or here, it's a multiscale element that you get when you run and look at the error. It's just a multiscale element. So it's a multiscale element that Ivan Graham has introduced as a coarse space already, which can be used. Or you can enrich it. So with 1 function per interface, 2 functions, 3 functions, 4 functions, and you observe if you go to 2 functions, things improve in iteration numbers as contrast goes up, but it's not robust. If you go to 3 functions, suddenly it's robust. It's robust because you have at most 3 inclusions that cross the interface. So you need 3 functions for 3 inclusions. But you can do it adaptively, like Axel said. If there's just 1 thing crossing, one function is enough. And so you're also robust if you do adaptively one function on one, 3 functions if there are 3. This is an example for a multiscale coarse space. We call this SHEM, spectral harmonically enriched multiscale coarse space, and it's exactly what I described for the Laplacian. It's Q1 functions plus sine functions, and here it's multiscale functions plus solutions of local interface dimensional eigenvalue problems. So to conclude, I would like to remind you of the 3 differences that I tried to show. The first difference was discrete versus continuous. The second was contraction estimates versus condition number estimates. And the third one was coarse spaces. You can find preprints on my webpage, and I'd like to advertise. It's now the end of the summer. It's probably the last time I advertise this. At the beginning of summer, I complained with Siam that we only got 5 copies to give away of my little PD book. It's a little PD book, 150 pages. And then Elizabeth Greenspan said, yeah, it's okay, but if anybody wants a book, they just send me an email. So this is my little PD book. I like it very much. It has 4 main components. It describes the 4 main discretization methods for PDEs. There is finite differences, there is finite volume, there is spectral methods, and there is finite element methods. For each of the methods, there is the precise historical way how the method was found. Then there is a complete convergence proof, stripped bare down to the bones, so you can basically just do it on the board. There's no result needed from any analysis book. It's worked out in the simplest, most setting, but it contains all the pieces that are needed in a general setting as well. It's just simplified. And for each method, there is a little code that you can try to play with. And if you send Elizabeth Greenspan an email, it seems she sends you a free copy. So thank you very much.